Hi everyone, today I'm going to present the rising bubble. As you can see here in this video, I will try to code with you the code of rising bubble. So basically you have a bubble in the pool and you just let rise the bubble like in this video. So in this course I will talk about some dimensionless number, as you can see in the left side, the bond number, which compare the gravitational effect with the capillary effect, and the Galileo number, which compare the gravitational effect with the viscous effect. So in this code, I will assume the geometry is axisymmetric. So I will work with r direction and z direction, and I will assume in the theta direction is constant. To simulate this problem, we need to recall some governing equations. So in red, the first equation is the Navier-Stokes with the second one also. With D is the deformation tensor. So U is the velocity field, P the pressure field, mu the dynamic viscosity, rho is the density, G gravity. The last term in the first equation with gamma, kappa and delta is the surface tension. So this term allows us to include the surface tension as a force directly in the Navier-Stokes equation. And also I will use the volume of fluid method to track the interface. So I need a third red equation, as you can see here. It's the advection equation just to see my interface. It means I will use the two-phase flow solver on Basilisk. So if I go in the website of Basilisk and I see the solver and function, as I said, I need the Navier-Stokes formulation, centered formulation. So it's incompressible Navier-Stokes solver, as you can see here. And of course, it's open source. So if you are curious, you can just read this page and read the code if you want to understand how can you implement the Navier-Stokes. And then I said it's a two-phase flow. So I need the solver of two-phase flow. And to do that, I just need to go in this one. As you see, I will use the volume of fluid method. Okay, so first I will just create the file. Okay, so let's call it rising.c. As we saw in the previous video, in Basilisk, when you want to start to code, you just need first to call some library by using include, like that. So hashtag include, because it's C, as you can see here, and which include you want to add. So first I said it will be an axisymmetric geometry. You can find the axisymmetry here, okay? And you can just read if you want. Just be careful when you use the axisymmetric coordinates, you will inverse the direction. So now y is the r axis and x will be z axis. So you just need to be careful. It means for the gravity, when you want to set up the gravity at the bottom, usually you will use y when it's 2D simulation, but when it's 2D axis, it will be x, not y, because you inverse when you use axisymmetric coordinates. So I need first to include the axis.h. The second one will be, of course, the Navier-Stokes solver, centered formulation. Then I said it's a two-phase flow simulation, so you should keep this order. First, the geometry. So if it's 2D, you just ignore this one and just write this one in first. But if it was in 3D, you need to use the include and the correct file for the 3D simulation, and then Navier-Stokes centered.h. And after that, you want to simulate the two-phase flow, so just call two-phase flow solver, like that. And then I said I will call the surface tension as a force directly included in the Navier-Stokes centered.h To do that, another include, and finally another library just to output our data after the simulation. Okay, we finished to implement our libraries. So now we just need to set up some variable, so some physical parameters. For example, the dimensionless number, the size of the box, and so on. Okay, so here you have the Galileo number, bond number, the density ratio, and the viscosity ratio. The box size, the radius of the bubble, and this command is just to define a max level for the mesh refitment, because I will use the adaptive mesh refitment. First, I will set up the size of the box. So to do that, just size, bracket, and the value of the size. So I use this variable and I just copy paste like that. And don't forget this one. I can set up an origin if I want to put your reference at the center, at the corner. So okay, I can also set up the init grid. So for the first step, which value of my grid I would like. So to do that, just init like that, grid, and you just need to set up a number, power of 2, of course. So let's try, for example, this one. Now I can set up the physical parameters. So you have the first density, row 1, equal just to 1, because I use the dimensionless number. For the row 2, is just equal to row 1 divided by the density ratio. And I do the same for the viscosities. For the surface tension, the keyword is f.sigma equal, so just 1 by bond number. And then I can just run this program to use this keyword, run. So now the next step, if you remember, is the initial condition. Okay, so as an event, as you know now, event init, like that, t equal to 0, bracket. And here I will just use a special function. The name of this function is fraction, okay? And when you use this one, you will set up a geometry of your interface when you use the two-phase flow solver, okay? So the first argument is f, the name of your interface, it's called f. And here you will just put the geometry of your interface. If you want a flat interface, circle interface, cube interface, whatever you want. So you just need to put the geometry here. For us, in our case, it will be a circle because it's not 3D, so it's not a sphere, but a circle. And to do that, you just need to remember the circle equations. Okay, so the circle equation is, of course, square of x, square of y, minus square of radius equal to 0. So you need to put it like that. But like as I change the reference, so I need to move the initial position of my bubble, and don't forget, as it's axis symmetry, the z direction, it's not y, but it's x, okay? So if I want to move in the vertical axis, I need to play with x direction, okay? So to do that, I will just define another variable. And okay, so my box is equal to 20. Let's put it minus 9. Why? Because the box size is equal to 20, okay? And here with this one, you will go to 10 to minus 10, okay? So if you put minus 10, you will not be able to see the bubble, but minus 9 is perfect because the radius is equal to 0.5. So you just need to modify something like that. And that's it for the event init. Okay, so just here is the gravity. To include the gravity, you just need to introduce another event, the name of your event, and when you would like to include the gravity. So here it means I would like the gravity each steps. Here, as it's a dimensionless number, so I just set up the gravity at 1, and why it's in the x direction, be careful because it's axisymmetry. Okay, and then I will just I need to call the adaptive mesh refinement, so like that. Okay, so this is the name of this function, adapt wavelet. So I would like to use this refinement in the volume fraction f and the velocity field u. In 2D and 2D axisymmetric, I have only two components of the velocity field, so that's why I have ux and uy, okay, and only one component because it's a scalar equation for the volume fraction. And here it's the keyword of max level, okay. And if I would like a mean level, it means I can say, okay, in the important region, I would like to use a big refinement, but in the region where is nothing, I would like to set up a minimal refinement. I can do it also. And finally, I can call this function, it's like a bar processing, as I said in the previous video, and this one just to extract the data in the V2 format. So the code is done now. I can just run the simulation by using QCC, something like that. And don't forget also to run your code by using this one. Okay? Okay, when your simulation is done, you just need to go in the paraview, as you can see here, open your data and select the volume fraction, for example, the field. And as you can see, here you have your bubble. I can play the video and you see the rising bubble, of course. You can also see the velocity profile. So if I zoom, for example, like that, you see the evolution of your bubble in the time. For example, I can apply a filter just to smooth the interface, like that. Okay, I can turn the geometry to see the bubble it rises in the vertical direction, as you can see here. I can also, for example, remove this part to do that. Okay, for example, you use the clip filter. You select Y direction, for example, and you just need to set up a number, for example 3. You will see it will move like that. I can put also 2, maybe 2 is better, something like that. Don't show the line, so you have something like that. I can reflect also this one, or maybe it's better if I use the transform filter. You will see why. So transform filter like that. I will use something like that. Okay. I will show you both. Remove show box, and for example at the right side, no, this one, yes, right side, for example, I want to show the volume fraction. Left side, I would like to show the velocity profile, for example. Let's just update for each iteration the scale of the velocity field. I can use also a contour to show the interface in the left side. And don't forget to reactivate this one. I can increase the thickness of the interface. Here, for example, let's do it with 2. Okay. The coloring, I will just set up the solid color. Okay. And for example, you will see something like that. Of course, you have the color bar of the volume fraction, velocity field, and if I play, here is a simulation for the rising bubble. Of course, the code will be available directly in my sandbox on Basilisk. So if you go in the play in the sandbox here, you just need to find me, and here is my sandbox. Go to the readme, and I will put the code directly on my sandbox. So don't hesitate to visit it. If you didn't understand something, of course, don't hesitate to write a comment. I will answer you, of course. And if you understood everything, so it's perfect. Okay, so thanks to watch this video, and bye bye.